If you are not a Part 3 student, actually, well, say for example a graduate student or something, you'll just have to come to your own arrangements with David. He probably won't mind. Right, so what we should do now is to look at some other black hole spacetimes. So I'm going to look first of all at the Reissner-nordstrom solution. This is a space-time which is static and a solution of the Einstein-Maxwell equations. Derived in much the same way as we derived the Schwarzschild metric. So the thing is also spherically symmetric. By Einstein-Maxwell equations, what I mean is Einsteinian gravity coupled to an electromagnetic field and nothing else. Now, that means that I have to invent the energy-momentum tensor for the electromagnetic field. And that is going to be equal to TAB, and I would like that to be 1 over 4 pi into FAC FBC minus a quarter GAB FCD FCD, where F is the electromagnetic field strength tensor. Now, it was at this point that I realized that there might be a minor confusion. Does everybody know where this comes from? From varying the action with respect to the metric. Okay, so we don't need to bother with that. So all we need to do then is to write down what the metric and the electromagnetic field strength tensor is. The easiest thing to do is to pick t, r, theta, phi coordinates. Oh, well, there is one thing which I should say about this. It might be that you don't have a 1 over 4 pi here, but you actually have a 2. This 4 pi has been put in to make life easy for you, so that there are no horrible factors of 4 pi appearing absolutely everywhere. So you pick t, r, theta, phi coordinates. We would like FAB to be defined in terms of a vector potential, which is dAAB minus dBAA. And the simplest thing to do is to just imitate what you would do if you were going to look at a point charge. So A0 turns out to be Q over R, and the line element turns out to be ds squared is minus into 1 minus 2m over R plus q squared over r squared dt squared plus the same thing to the minus 1 plus q squared over r squared So at this level, this just looks like a very, very trivial change to the Schwarzschild metric. You can interpret Q as being the charge because A0 is equal to that. So the only non-vanishing components of the F field will be FR0. That you can think of as being the radial component of the electric field, and that is going to be equal to Q over R squared, which slightly perversely with my sign conventions has got a minus sign. So Q really does represent the electric charge of some isolated object. You'll notice that as R goes to infinity, this thing just tends to the Schwarzschild metric. That's because this term dies off more quickly than that one. So M represents the mass of whatever it is. So that is the line element for the Reissner-nordstrom metric. Now we have to deal with the issue of singularities. It is not too surprising to discover that at R equals 0 you have some kind of horrible curvature singularity. Not only is it a curvature singularity, but you can see that the electric field blows up there, and you know that if you were going to do ordinary electrodynamics without worrying about general relativity, you wouldn't worry about this because you'd say, oh, well, I'm going to construct some finite object which is the source of charge and that will get rid of singularities. It is not so easy to do in the case of general relativity, so we will just simply look at this and perhaps if we have time return to the question of charged bodies later. So Maxwell's equations also break down as R equals 0. So and the Einstein equations break down. But that's not very much different to what happens in the Schwarzschild metric. There are, of course, other sources of singularity. There are the possible zeros of this function here. Those, unsurprisingly, correspond to coordinate singularities. So if 1 minus 2m over r plus q squared over r squared is equal to 0, then, well, you have to do a calculation to prove that it really is a coordinate singularity, but we'll do that. But if it does equal to 0, then there are coordinate singularities. These will, of course, happen when r is equal to m plus or minus the square root of m squared minus q squared. Now this of course brings us to a very important point. If you think about this, this means there must be 3 separate cases. Suppose that m is bigger than the modulus of q. I was going to take m to be positive. More about that later. Suppose that m is bigger than the modulus of q. Then there are 2 distinct zeros, which I'll call r plus and minus. Then there is case 3, which is m is less than the modulus of q. Then there are no zeros, And lastly, there is case 2, where m is equal to the modulus of q. Of course, you have to be lucky to get to this stage. So that tells you that this term goes to 0, and what you actually have is sort of coincident zeros. So if m is if m is greater than the modulus of q, you have two distinct zeros, and they're both simple zeros. But in the case of m equals mod q, it's a double zero, so it's a sort of minimum of this function. So these are sort of, I'll just call it a degenerate case for the time being. It may look exceptional, but it actually turns out to be very interesting. So we really have to divide up what we're going to do into 3 entirely separate cases and treat them all separately. So let's start with case 1, where you have 2 distinct zeros. So this is an interesting sort of generic case. If you stare at this metric here, what you learned before when dealing with the Schwarzschild metric is that a simple way to deal with these coordinate singularities would be to invent some null coordinates, which I called v and u. So it is not unreasonable to guess that the same trick is going to work if I deal with this slightly more complicated metric. That turns out to be true, and the easy way to do this is just to say, well, I'm going to invent, I guess to start with, a retarded time function u, which is equal to t minus some function of r, to be determined to make life easy for ourselves. So that means that du is dt minus f prime of r dr. And let's call this function here v of r. Our metric will then become minus v into dt squared. dt is du plus f prime of r. Then there's a dr squared over v plus r squared d omega 2 squared. So if I multiply that out, what will happen is that you'll end up with a simple form of the metric, which you can make just like the Eddington-Finkelstein form of the Schwarzschild metric. So ds squared will be equal to minus v du squared minus 2v f prime du dr, and then plus dr squared into 1 over v minus f prime squared plus r squared d omega 2 squared. So obviously I can make this look like the Schwarzschild metric in Eddington-Finkelstein coordinates by getting rid of the dr squared term, namely this one. Then I'll just have a du squared term here and a du dr term. So choose f prime to be equal to 1 over v, so this term vanishes. And then we're just simply left with the same kind of thing that we had before. ds squared is minus v du squared minus 2 du dr plus r squared d omega 2 squared. Obviously I can do the same thing with an advanced time coordinate rather than a retarded time coordinate if I wish to.
Sorry, why isn't that f dash squared?
Something silly has happened. The v f prime squared. Is that right? Yes, that is right. So that's the answer. So this is the form of the metric. It's worth our while explicitly looking and seeing what happens if you try to find what this function f is. The easiest way to write v in this case, where you have two distinct zeros, is to say, you could do it in terms of m and q if you wanted to, but the easiest way to write it is just to display the fact that you have simple zeros at r plus and r minus. So just as good a way of writing it is r minus r plus times r minus divided by r squared. And that will make your life a lot easier, then there won't be square roots of m squared minus q squared everywhere. So df dr is therefore equal to r squared over r minus r plus times r minus, and all you have to do is to integrate that up. And you will get f is equal to the integral of r squared dr over r minus r plus times r minus, and that is, after a little bit of effort, r plus squared over r plus minus r minus times the logarithm of the modulus of r minus r plus minus r minus squared over r plus minus r minus times the logarithm of r minus r minus. This is a bit of a mess. I do not expect anybody to remember a formula like this. What is important is to remember how to derive it. The derivation is simple. You invent a coordinate transformation which makes life easy for you and gets rid of this horrible term here. And you can see that a byproduct of that is that if you pick a line of u theta phi constant, well, if u and theta and phi are constant, it's only moving in the r direction, and you can see that motion in the r direction under those circumstances is null, because if u and theta and phi are constant, theta and phi constant makes that equal to 0, u equals to constant makes this equal to 0, and so it's null. So that corresponds to an outgoing light ray, just as it did in the Schwarzschild metric. As you might expect, there is something funny about this function when r equals r plus and when r equals r minus. That's because this thing will blow up there, or this thing will blow up here. But you can see that we have got rid of all the coordinate singularities, because in this form of the metric, whilst it's true that v is equal to 0 at r equals r plus and r minus, the metric in the UR plane is not degenerate, it's perfectly invertible and is perfectly smooth. So there are no coordinate singularities at either r equals r plus or r equals r minus. We have achieved our aim. Now, suppose that I now look at the space-time that results from this. Well, what I've done is I picked u, r, theta, phi coordinates. And so if I try to draw a Penrose diagram of what is going on here, without worrying too hard about the details of this, so I'm going to just consider the UR plane, as is usual for this kind of thing. Obviously, I should warn you, this diagram is infinite in the vertical direction, so you may want to do this on a new piece of paper with this bit in the middle. So there is an exterior region where everything is asymptotically flat out in this direction, as it would be for the Schwarzschild metric. So you can construct the usual kind of scri plus, I0, scri minus here. And if I ask myself about lines of constant u, they're constant retarded time, and they would look something like this. And you would quite happily go through this surface here, which corresponds to r equals r plus. In the past. That much is obvious. You can see that r equals r plus is indeed a null surface. You fix theta and phi, gets rid of that. At r equals r plus, r is constant, v is 0, so it must be null. So it's perfectly legitimate to draw it in that particular way. But now you can see that something different to what happens before is going to happen. If you move in this direction, r is decreasing, and r equals r plus is null. You can keep going through the r equals r plus surface, and r continues to decrease, and what will happen is you'll discover a place at which r equals r minus, and it's null again. So there is another surface down here, approximately there, where r equals r minus, and it's another null surface. Now it's a little stupid that I erased the original coordinates, so I'll return them. My v seems to have disappeared as well. So if you stare at this form of the metric, what you will see is that v is positive in this region, but negative in this region. So, because it's positive in this region, surfaces of constant t are space-like, surfaces of constant r are time-like. Whereas in this region, surfaces of constant t are time-like and surfaces of constant r are space-like. I suppose it is a good idea to try and draw how that happens. I can't remember what convention I was using before. Anyone remember? R was green and t was red, or was it the other way around?
T is green.
Constant t is green. All right. Let's remind ourselves of what's going on. Well, perhaps brown rather than red, but so in this region, then of course lines of constant t will look like this, as they would before, and here they'll be swapped round and look like this. In case you're worried about what t does, they're perfectly good coordinates, but they don't really join up on this surface, because at this surface t equals minus infinity. So assuming that you don't want to have horrible discontinuities, t runs from minus infinity down here to plus infinity up there, and minus infinity there to plus infinity there. Of course, it's not the same t. That means, of course, fixing t and r does not fix you at a point in space-time. So you have that region. And if you drew lines of constant r, of course, they'd look the same kind of thing the other way around. So they would look like this. So, suppose I am here, when you ask where you've come from, well, you could have been in this region all the time, but you could have simply emerged from there. But there's no obstacle to coming through this surface. So you can go through this surface r equals r minus and find yourself in yet another region of space-time, and that's quite different to what happened in the case of the Schwarzschild metric. Perhaps even worse, you'll realize, of course, that there is nothing that's going to stop you going to decrease r further until you get to r equals 0. At r equals 0, well, for r very small, v is obviously positive. That's because this term is negligible compared to that one, and of course and that one is negligible compared to both of them. So v just looks like q squared over r squared, close to r equals 0. So that tells you that r equals 0, instead of being a space-like singularity, is in fact a time-like singularity. So you can reach the surface r equals 0 here, and it looks something like that. Let's get rid of this white line. It's not very nice. Not so easy to get rid of, actually. So if you try to draw these lines of constant t, they would look something like this. And lines of constant r would look something like this. So that as r goes to 0, you end up close to this point. So the first huge difference is that there are two regions inside the horizon, one of which is just simply some peculiar region, and the second contains the singularity, which is now time-like. That's fine. You could, if you wished, have constructed VR theta phi coordinates in much the same way. And if you had done that with the same f of r, you would have ended up here with minus v dv squared plus 2 dv dr plus r squared omega 2 squared. Instead of then extending this region, the original exterior region, to the past, as you did here, you would extend it to the future. Otherwise, it would look the same. It's very similar to what you did in the Schwarzschild case. So if you extend this to the future, you will end up with, again, two regions. This would be r equals r plus. This one here would be r equals r minus. And then you'd find something that was singular here. So this surface is r equals r minus, and this surface is r equals r plus. And again, if you constructed lines of constant t and r in these regions, they would look something like this. So, if you stare at this picture, you will now realize that there is something missing. If I started off in this region and went here, then of course this is to the past of this region, I can leave it by going in this direction, but of course it looks like I can leave it going in that direction. So it looks like there ought to be something there, analogous to what happened in the Schwarzschild case. The way to find the something there was to construct Kruskal coordinates about this point. So the next question you need to ask is, can you find the analog of Kruskal coordinates, which allows you to get rid of the singularity for finite t and r goes to r plus at this point? The answer is yes. Near r equals r plus, you can define Kruskal coordinates u plus and u minus. Sorry, u plus and v plus by the following. Little u is equal to 2r plus squared over r plus minus r minus times the logarithm of the modulus of u plus or minus. And no, I think that's fine. And v, oh no, that's fine. That's plus. V is equal to, I think I need a minus sign there to make it work. 2r plus squared over r plus minus r minus, the logarithm of v plus modulus. The important point about this is that it can be done. Again, I don't think that I expect anybody to remember this. It's just simply that something that you can do if you need to. If anyone actually wanted you to construct the Kruskal coordinates, I'd almost certainly tell you how to do it. In Kruskal coordinates, what happens to the space-time metric? The answer is ds squared equals minus r plus over m all squared e to the minus 2mr over r plus squared, the modulus of r minus r plus to the r plus squared plus r minus squared over r plus squared du plus dv plus over r squared plus r squared d omega 2 squared. Wrong. R minus, not R plus. That is R minus. You can tell that it has to be R minus. Nothing peculiar happens at R plus. At R equals R plus, this thing turns into R plus minus R minus. That's fine as long as they don't coincide, and so there is no problem. So this metric is well defined at R equals R plus. So that means that you can construct around this point a set of Kruskal coordinates that does exactly the same thing as happens in Schwarzschild, from which you can conclude that there is a region here which is another asymptotically flat region which sits out here, which cannot communicate with this thing. So for this region you construct u plus v plus coordinates. Well, that's half the story. If you ask about the metric in this region, well, the metric in this region in tr theta phi coordinates is of course the same as the metric in this thing in tr theta phi coordinates. The metric here is just the time reverse of there. If you ask about the metric here, well, again, it looks like there's something missing, because if you were in this region, not only could you have come in through here, you could have come in this direction. And you know that something is peculiar, because this point here looks like there is something missing. So you need to invent u minus some different Kruskal coordinates, u minus and v minus, to get you around that point. It's almost exactly the same as you did over here for u plus and v plus. And in fact, all you have to do is to change a few signs. So you can define a u minus and a v minus. U is equal to 2r minus squared over r plus minus r minus times the logarithm of u minus modulus. V is equal to minus 2r minus squared over r plus minus r minus logarithm of the modulus of v minus. And if you want to find the space-time metric, it is ds squared is equal to minus r minus over m all squared e to the minus 2 mr over r minus squared, the modulus of r minus r plus to the power r plus squared plus r minus squared over r minus squared du minus dv minus over r squared plus r squared d omega 2 squared. So if you stare at it, it's very, very similar to the u plus v plus coordinates. Again, I must emphasize, I don't expect anyone to remember that.
What's the Milbert metric?
Sorry, what is the what?
The r plus plus r minus over r minus squared.
Yeah, you want the minus and pluses switched. The exponent on the middle.
Here?
Yeah. You have r minus over r minus. You want r plus over r minus.
That's what I want. Oh, missing, same story up here, missing brackets. Sorry. So nothing peculiar happens at r equals r minus. But now that's the same story. Around here, you link 4 regions. So you will be able to conclude that, in fact, what you've got is something which looks like this. So it enabled you to construct some region to its past and another singular region. Similarly, up here, because this is the surface r minus, so you can construct another 2 regions there. Now, of course, you can see why this diagram is infinite. If I ask myself about the metric in, let's start with this region. The metric in this region is the same as the metric in that region. The metric in this region is the same as the metric in that region, but time reversed. The metric in this region is the same as the metric in that region, but time reversed. The metric in this region is the same as the metric in that region, but time reversed. A consequence of which is that the metric in this region must be the same as the metric in, is it right? Past of that one. That one. Similarly, the metric in this region has got to be the same as the one in that region. And hence the metric in that region is the same as the one in that region, and so forth. Yet, in each case, I have got to come from somewhere, and I have got to go somewhere, which means that the obvious thing to do is just to continue this diagram forever. So the consequence of that is that this diagram becomes infinite in both directions, and you're left with a structure that looks like this. Well, it gets harder to draw, actually, the further you go. It's important, well, maybe it'd be kind of a bit late to tell you this, it's important to make sure that your areas are more or less square when you draw this, otherwise it won't match up properly. Well, I guess it doesn't matter about there anymore. And then similarly up here, it goes on forever. So, there are, in the Reissner-nordstrom solution, an infinite number of asymptotically flat regions, here, 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 all the way up. An infinite number of singular regions, here, 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 and so forth. And a sort of infinite number of regions which are interior to R plus and R minus, like here, 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 and so forth. So the complete space-time of the Reissner-nordstrom metric is, first of all, amazingly different to what happens in the case of the Schwarzschild metric. So, infinite number of asymptotically flat regions. An infinite number of singular regions. Well, that's all the same things. Two, time-like singularity. Time-like singularities don't have the same intuition associated with them as space-like singularities. And that's easy to see. Just contemplate the following causal curve. So let's suppose that I start off in some asymptotic region, say here. There is absolutely nothing stopping me moving in this direction to that region, which is obviously behind some kind of black hole horizon. But I can hover arbitrarily close to the singularity, and I'm not forced to crash into it. In the case of a space-like singularity, I was forced to crash into it because if I moved in along a causal curve, I had to meet the singularity. Here I can get quite close to it, probe it, and then if I wish to, simply go away and enter another asymptotic region like that, and you would feel quite happy. You wouldn't have done anything unphysical by doing that. So the sort of nature of time-like singularities and their consequences is quite different to space-like singularities. So that is the basic nature of the Reissner-nordstrom solution. You might decide, hang on a minute. This kind of path, where you go into a black hole, travel through some interior region and then emerged to another asymptotically flat region has been exploited by a vast number of science fiction writers who seem to think you can use black holes to do whatever you like. You can see that if this is the correct picture, you can't. Because whilst it's true that you could start off here and travel in this direction to this asymptotic region, this of course is not the same region as the one you started off in. So you could not get back home. You'll be forced to move in this direction, always towards the future. That, however, brings us to another point, also much loved of science fiction writers, which is the following unfortunate mathematical fact. Which is that I can chop up this picture. So let's contemplate what happens if I do that. So here is the surface t equals 0 in this region. Here is the surface t equals 0 in this region. So I could simply chop off everything below here and everything above here. And if you calculate the metric on this surface, or in the neighborhood of this surface, they of course match up exactly. That means that I can glue together the resultant space-time and find something which doesn't have a boundary in the future or past in the following way. I could decide that. I always find this a bit hard to draw, actually. So I could decide that was all of the space-time that I was going to have, with the proviso that this surface here and this surface here were identified. That is to say, I call them the same things. That is a perfectly reasonable space-time. It is absolutely smooth. This join is completely and utterly invisible because the metric close to here is the same as the metric close to here. This space-time, being smooth, only having singularities here, has an obvious pathology, namely it violates causality. Meaning, suppose I move in a causal direction, so I start here, I move to the future, say like that. That's the same point as this one. I can come back here and arrive here. This blue line is a future-directed time-like curve everywhere. So I have started off here, moved to the future, and found myself in a position shortly before I left. If you are allowed to do that, then of course you can meet what is usually called the grandfather paradox, namely that you shoot and kill your ancestors at this point, and therefore how can you have started off? I do not know how to resolve that paradox, other than by saying it can't happen. Yes?
What about your proper time when you move along this curve? So
it's fine.
Is it finite?
Can be. Yep. I don't think I can say anything stronger than that. Now, that doesn't bother me so much as the following. So what has happened is I found a solution of the Einstein equations which violates causality in this gross way. That, unfortunately, would appear to be a counterexample to the idea that the Einstein equations are sensible. That is to say, there's nothing in the Einstein equations that tells you have to have sensible causal properties.
In this sense, you're violating the causal structure by some topological things.
Yes.
And the Einstein's equations are looking at local things on metric scale.
I'll find you another one. I'll tell you about another one. Well, maybe you already know about another one. So this is perhaps, or in this particular case, you decided to do it by this cutting and pasting operation, and of course you didn't actually have to do that. So you can get out of it in this particular case. So this is a relatively okay case. It's relatively easy to resolve. I don't want to put it more strongly than that, but whether you decide to do it or not is entirely and utterly up to you. So you can either do it this way, where there is no problem, but you have lots of asymptotically flat regions which are all different, or you can do it this way and violate causality, and I don't really care which. That's probably a good place to stop for today.